Let's start the presentation of ReConPatch. I am Hyun in AJI Research. Its table of contents. Vision anomaly detections aims to identify and locate irregularity within a dataset using only normal images for training. The challenges in anomaly detections are unpredictable anomaly type across the domain and limited training dataset, and diversity within normal datasets make it difficult to identify anomalies. Our proposed method, ReConPatch, tackles these obstacles by building contrastive learning-based representation learning model, and it effectively clusters normal data points while actively dispersing outliers. And finally, ReConPatch achieved the state-of-the-art anomaly detection performance for the MVTec anomaly detection dataset to 99.72% and the BTAD dataset to 95.8%. PatchCore is an algorithm that detects anomalies by extracting locally aware patch features of normal data without learning process by employing an ImageNet pre-trained model. It effectively stores the features of normal data and achieves high performance through locally aware patch feature and coarse subsampling process. They use local neighborhood aggregation when constructing each patch level feature representation to make it robust to small spatial deviations and to increase the resection field size. Therefore, they aggregate feature vectors that are neighbors as follows. Also, using multiple features hierarchies can help improve performance. To combine these two features, they binarily rescale the local patch feature vector except from layer I plus 1 to match that from the layer I and merge the corresponding patch features. And then use relative average fooling as a feature aggregator to make a coset to generate a memory bank. Memory bank updated by coset subsampling with greedy approximation sampling method. In test phase, PatchCore generates coset of test image and calculating anomaly score via distance from nearest representation feature of memory bank. So we visualize high-dimensional coset which generated by locally aware patch feature by UMAP with color coding indicating spatial position. We found that cosets extracted by PatchCore from the same position are not in the same cluster in the embedding space and are dispersive. We hypothesize the anomaly detection performance could be improved by clustering similar features of a normal image together and distancing non-similar features from each other in embedding space. Our framework consists of the training and the inference phase. In the training phase, we collect the feature map from pre-trained model for each input in the training dataset. The feature map have different spatial resolutions at the feature hierarchy of the CNN, so they are interpolated to have the same resolution before being concatenated. The patch level features P then generated by aggregating the feature vectors of the neighborhood within a specific patch size in the same approach employed in PatchCore. ReConPatch utilized two networks to train representations of the patch level features. Upper network are used to calculate pairwise and contextual similarities between patch level feature pairs. It is gradually updated by an exponential moving average. The bottom networks used for the representation learning of patch level features is trained through the related contrastive laws. The objective of ReConPatch is to learn target-oriented features from patch level features, thereby enabling more effective discrimination between normal and abnormal features. To accomplish this goal, a patch level features representation learning approach is applied to aggregate highly similar features while repelling those with low similarities. However, such training requires a labels pair to indicate the degree of proximity between patch level features. To address this issue, we utilize the similarity between patch level features using the pairwise similarity and the contextual similarities as pseudo-labels. The similarity is high, then the pair is pseudo-labeled as positive. At first, the pairwise similarity defined as equation number 1. It is used to measure the Gaussian kernel similarity between element I of P and J of P, which is widely used to measure anomaly scores. However, the pairwise similarity is insufficient to consider the relationships among groups of features. as shown in this figure. For example, case A and B have the same pairwise similarity. In A case, K nearest neighbor of I and J do not enclose each other. Therefore, contextual similarity is a lower value, and they should be separated. By contrast, in B, they belong to the same group and should be gathered. The final similarity between two patch level features, element I of P and J of P, then defined as a linear combination of two similarities, is defined as equation number 6. Patch level features do not have explicit labels because each patch image is correlated with neighboring patches. Additionally, the goal is to get unique target-oriented features. Therefore, the relaxive contrastive loss is adopted, which considers the similarity between features as pseudo-labels. Delta ij denotes the relative distance between embedding vectors in a mini-batch. The relaxive contrastive loss is defined as equation number 7. While representation learning networks are trained with relaxive contrastive loss, the similarity calculation network are slowly updated with the exponential moving average. Because the fast training of the similarity calculation network reduces the constants of the relationship between the patch level features and leading to unstable training. Anomaly scores are calculated in the same manner as in the case of patch core. After training, the course is subsampled from the newly trained feature representation F layer using the grid approximation algorithm and stored in memory bank. The course takes a lot of the representative feature, which is used to compute the anomaly score. The pixel-wise anomaly score is that obtained by calculating the distance between the representation layer output and its nearest coset within the memory bank. And the image-wise anomaly score is computed as the maximum score over the anomaly score calculated for every patch feature in the image. The accuracy of anomaly detection could be further improved by score level ensemble for multiple models. To compensate different score distribution of each model, we normalize each score using the modified Z-score. The experimental result. On MVTec dataset, ReConPatch achieved the best detection performance of 99.72% in the ensemble model, and also achieved the best performance of 99.62% and 99.56% in the single model. Following is the segmentation result. The orange line is the ground truth of the anomalies. The green star is the maximal location of the anomaly score in the heat map. We experiment with ReConPatch to verify its performance. At first, we tested changing the dimension of the F layer, indicating that the highest performance was achieved with a dimension of 512. We note that even with 64 dimensions, ReConPatch outperforms patch core, which supports the dimension reduction capability of our method. To simulate real-world scenarios, we randomly applied data augmentation to test the dataset, while patch core's image level performance decreased to 3.62% under these conditions. ReConPatch only slightly decreased to 1%. ReConPatch effectively trained the representation by applying the metric learning, which is software guided by the similarity over the nominal features. Applying the contrastive learning with two similarity-based pseudo-labels, ReConPatch shows the state-of-the-art performance on the MVTec anomaly detection dataset. ReConPatch is robust to these environmental changes that may occur in real industrial scenarios by learning patch level feature representations. Thanks for listening.